So thanks, Fritz. So setting us up, it's negative du. Well, now I need u to be cosine. That is good. That is good. But now I have to deal with that sine squared term. That's not taken care of by u. It's not taken care of by the du. And so because of that, I need to rewrite that sine squared that I put in highlighted. And this is where I need to use Pythagorean identity for. And I want to use that because eventually I want to use a u substitution where u is cosine. Well, that sine squared that I highlighted, that's a big issue. Can't leave that there. So I rewrite it in terms of cosine by my Pythagorean identity, so I don't have to worry about that anymore. And now after that step, I'm ready to do a u sub. Where u is cosine of x. Then du is negative sine of x dx. Don't have the negative part, but I'm only off by a constant. So I don't need to adjust much. Everything is good to go. I'm ready to do a u sub. So original problem that I had originally, what I'm going to get after subbing is integral 1 minus u squared, as I now have u to be cosine, times another u squared for that cosine squared, times negative du. And now I finish up. Distribute that u squared to give me u squared minus u fourth times negative du. Distribute again that negative sign to what I currently have. That'll just change the order to now u fourth minus u squared. The power rule for antiderivatives is add 1 to the old exponent to get the new exponent, divide by the new exponent. That should be a minus. I evaluate it, so I do a plus c. And also, because I did a u sub, and I'm doing it on an indefinite integral, I have to rewrite in terms of the original variable. So cosine to the fifth minus 5 minus u cubed over cosine cubed over 3 plus c. And that's my general strategy if I have an integral of sines and cosines being multiplied and one of them has an odd power. Main remark I want to make at the very beginning. If cosine had the odd power, I would do the exact same thing, but I would take a cosine away, rewrite that cosine squared as 1 minus sine squared, and then I would do a u sub where my u was sine. So if I had this type of integral with sine and cosine being multiplied, first question I ask myself, does one of them have an odd exponent? If so, take that odd exponent, group it with the dx. That forms my du. Rewrite the leftovers in terms of 1 minus sine squared or 1 minus cosine squared. Then do a u sub to finish up evaluating your integral. Any questions about that in particular for trig integration? Perfect. Now here comes the next question. What if both have even powers? So instead of one of them having an odd power, let's say this is my new scenario I got. Where now I'm integrating a sine and cosine, but both of them have an even power now. I can't do the trick I did before, which was take away one of the powers away from it. So let's ask you this. If I have a sine and a cosine integral, and if both of them have an even power, what should I do here? Try to help me out. Or better yet, what trig identity would help me here to try to evaluate that integral?
The double angle identity.
Double angle identity. It's called the half angle identity, Matthew. But I know what you mean when you say double angle identity. And I think you mean this identity. And that's just me clarifying. Is that what you meant, Matthew?
Yeah.
Okay, yeah, these are called half angle identities. The double angle is if I had like cosine of 2 theta or sine of 2 theta. But in this scenario, as long as you know them, I don't care what you call them.
Okay.
So the idea here is, as Matthew mentioned, these are the identities I want to use. And kind of the dot process is I want to kind of treat it like polynomials, try to multiply and simplify as much as I can to try to make this work. Now, before I do that, and use the half angle identity, I do need to rewrite one of them, in particular the sine to the 4th power. And I'm going to rewrite that as sine squared, all of that squared beforehand. The reason why I'm doing this step first, before I use the half-angle identities, is to make it clear how I'm going to use it here. So because I had sine to the fourth power, what's going to happen is I'm going to plug in or substitute in the 1 minus cosine of 2 theta, all divided by 2, inside that squared. And then just like with a polynomial, I'm going to multiply it by itself to try to evaluate it. So now here I'll use the half-angle identities. Sine squared x, 1 minus cosine 2x all over 2 squared multiplied by half-angle identity for cosine. 1 plus cosine 2x all over 2. Two squared will give me 4. Multiplied by that 2 will give me 8 in the denominator, which means I'll have a coefficient of 1/8, 1 over 8. And one of our properties of integrals, coefficients or constants, I could take those outside of the integral and multiply it to it. So that's where the coefficient of 1/8 came from. And so now what I have in my integral is 1 minus cosine of 2x, all of that squared, times 1 plus cosine of 2x. And that's going to be the main integral that I work with for here. Any questions about how I got to this step? Okay. So from here, I'm not going to give y'all a chance to practice. So starting from this line, I want you all to try to evaluate this integral on your own. Keep in mind that, like I said, for that integrand, think of it like a polynomial, where I got to FOIL stuff out and then simplify and all of that. So I want y'all to keep in mind for that. One hint that I want to give y'all before you begin evaluating. And it's going to seem silly for what I'm doing. But my advice when you start doing the multiplication or boiling is it might be advantageous to start evaluating that guy first, instead of doing the 1 minus cosine of 2x squared. So that'll be my advice with that. Okay. So again, from here, go ahead and try to evaluate the integral. I'll give you all a few minutes to work on that. If you have any questions, let me know, and I'll be more than happy to pop in. And right now on my end, I got sys 24. Let's say at sys 30, we come in, we reconvene and work this problem out together. All right, so I'll let you finish this integral up and see what y'all get. And Sis30, we'll reconvene and do this problem. All right. Give me a status report, y'all. How's this problem going?
I foiled everything out and got 1 minus cos 4 2x plus cos 3 2x. I got stuck.
Okay. We can work that out. Okay. So it's this 31. So let's work this out. First thing I want to note, there's a reason why I suggest to do the foiled the first two out that I highlighted. And the reason why is because at this part, there's a two square scenario going on. Because I have both the first and second slots being the same. Only difference is that one I'm subtracting, the other I'm adding. And the reason why that is nice to know is when I FOIL them out, what I'm going to get is the first term squared, so 1, the second term squared, and then all of that subtracted. So that takes care of the 2 highlighted. Now I need to FOIL out the 1 minus cosine of 2x and the 1 minus cosine squared of that 2x now. Doing that FOILed, I get first 1 outer cosine squared of 2x, inner last so after FOILing out, this is what I should get at the very end. 1 minus cosine squared 2x minus cosine of 2x plus cosine cubed of 2x. And my advice here is to tackle each integral individually. So that's what Yesnet's line is going to state. That I'm using the property of integrals that says I can look at each integral individually, join them together by addition or subtraction at the very end. So minus cosine squared of 2x dx minus integral of cosine of 2x dx plus integral cosine cubed of 2x dx close. That first integral, I'm not super worried about because that is the integral of 1. So that integral will just give me x at the very end. That second integral, the antiderivative of cosine is sine. And because I have a 2x as its argument, when I take its antiderivative, I would have to divide by 2 at the end. So I'll make that as a note. I already have what this integral will be. I also have what this integral will be. So those two integrals taken care of. These two integrals, however, are going to require a little bit more work in order to tackle them. So let's tackle them individually. First, let's tackle the cosine squared of 2x and try to integrate that. Don't have an odd power with it. I have an even power. What we talked about at the very beginning, I said if I have a sine or a cosine, and if it's only even powers, I got to use a half angle identity. Now, the caveat here is in that integral, I don't have just the angle or the variable x. I have 2 times x. That's not that big of an issue because what I'm going to do and what this identity says is I'm going to double whatever was inside the cosine squared to begin with when I applied that identity. So in that integral, I have 2x in there. So I will have to apply the half angle identity again because it is cosine squared. But when I do apply it, I will have to write 4 times x because I'm doubling what I originally had inside the integral. Split that guy up. First integral is the integral of a constant. So that will be x over 2. Antiderivative of cosine is sine. Because I have a 4 inside the argument, I would have to divide by 4 at the end. Meaning that for the cosine squared of 2x integral, after evaluating, I'll get x over 2 plus sine to the 4x divided by 8 plus c. Any questions about that integral in particular? Okay. So now we move on to the other integral that does require a little bit more work as well, which is the cosine cubed one. So first thing to note, this is still, even though I don't have a sine being multiplied to that this is still considered a trig integral with an odd exponent married with it. Even though I don't have a sine popping in somewhere, I will still count that as a trig integral with an odd exponent. So my strategy for cosine sine with an odd exponent now comes into play. And what that says is take 1 away from the exponent, marry it with the dx to get ready for du, and use Pythagorean identity to rewrite the cosine squared of 2 theta in terms of sine. Giving me now 1 minus sine squared of 2 theta times cosine of 2 theta dx. And now with that, I am ready to begin to u sub for this particular integral. So I'm going to set u to be sine of 2x. Then du, or the derivative, will be 2 times cosine of 2x dx. I am off by a constant, which means I'm going to have to divide that 2 to the other side in order to rewrite that. So du over 2 will be cosine of 2x dx. I now know everything that needs to go inside this integral. So now I'm ready to begin the u sub. Integral 1 minus sine of 2x times cosine of 2x dx by u sub will equal, that needs to be a square, 1 minus u squared times du over 2. I have a constant of 1/2. So I can take that out of the integral, giving me 1 minus u squared in the integral. Use the power rule for antiderivatives here to evaluate to give me u minus u cubed over 3 plus c. Recall what I called u to begin with, which is sine of 2x. And then now I distribute back the 1/2 to each of them, giving me at the very end, for that second integral I had to work hard on, sine of 2x over 2 minus sine cubed of 2x over 6 plus c. Any questions about this particular integral and our work for here? All right. So now, going back to here, we've now tackled those other 2 integrals. So now I'm ready to finish the evaluation overall. So copy, paste. Oh, well, that'll work. So now, this integral overall will now equal, putting all the pieces together, 1/8. We got that 1, that antiderivative would just be x, minus, let's go back up. We got that the integral of cosine squared of 2x will be x over 2 plus sine to the 4x over 8. Minus the third integral, which we got to be sine of 2x over 2 plus that last integral, which we just concluded above, so that would be sine of 2x over 2 minus sine cubed of 2x over 6. So sine of 2x over 2 minus sine cubed of 2x over 6 plus c. And you could simplify if you want, but because this is part of our answer, I do not need to simplify here. And this will be my final answer for that particular problem. Again, I didn't expect this to be as nasty as it has to be, but I want to reiterate from above. The main idea, if you have a sine and cosine integral with even powers for both of them, half angle identity to rewrite a sine squared into cosine squared, FOIL them out as much as you can, and then start integrating. Note, as we saw in this particular example, you might have to use half angle identity again, or you might have to use a trig integration with an odd power like we did for the last integral here. But at the end, the core of it is that rewrite using the half angle identities and then treat them like polynomials to FOIL out and then integrate term by term. And that's our game plan for that type of integral. Any questions about that in particular?
So if we're doing an integral that utilizes the half angle identity, all of the parts of the integral you have to apply the half angle identity to.
Right. So you would have to apply that to when you see a cosine squared and when you have to see a sine squared.
Okay.
Yeah. Now keep in mind that you might have to be a little bit careful, and I'll scroll back up to kind of explain what I mean by that. For example, the sine to the fourth. I rewrote that sine to the fourth as sine squared of x, all squared on purpose. So that way I made sure I didn't mess up when I applied the half angle identity. And to note that in my next line, that overall thing in pink would be squared. So when you do apply the half angle identity in this scenario, do be a little bit careful if you have, say, sine to the fourth or cosine to the fourth or something like that. And note that it will all have to be squared.
Right.
Right. All right. Any other questions about trig integrals with sines and cosines in them?
Are we going to be given one that's a trig integral and trying to determine if it converges or diverges?
No, that's too mean for y'all because that's an
Okay.
improper integral combined with a trig integration. I think for a 90-minute exam, that's a little too mean. And I think
Thank
that's
you.
as much as I can say before to not get in trouble with Dr. Burr, that we are nice enough not to do that because I think that's too hard of a problem for a test.
Well, I don't think anyone here would report you.
Wonderful. All right. So the other type of trig integrals are tangents and secants. So let's talk about those real quick. So unlike with the sine and cosine scenario, where there's sort of a lot of symmetry to them, for the tangent and secant integral, there's a little bit of subtle difference between the two of them. And again, I'll explain both of these scenarios with examples. So the first scenario in your trig integrals with tangent and secant is that the power that is married with the secant is even here. So if you have a tangent secant type integral where the secant power is even, I'm going to do my strategy like I did before with the cosine and sines of taking one away. However, instead of taking one secant away, I'm taking away a secant squared here and marrying secant squared of x with the dx. Now, the reason why I am taking away a secant squared instead of just one secant is because just like before, I want that part in pink to be my du when I perform a u substitution. And for this particular thing, u would be forced to be tangent of x. And back in Cal 1, the derivative of tangent is secant squared. So that's why I'm taking away a secant squared instead of a secant away from it. So I can have that free, automatically set as my du, where u is my tangent. So for the u sub, well, that's good. That's going to be u. That's Gucci. That's going to be du. That secant squared is not good. I can't do a u sub yet because of that secant squared. So I need to rewrite that secant squared just like before. I need to use an identity to rewrite that secant squared in terms of tangents. So what do y'all think? Which trig identity should I use to rewrite that secant squared?
Isn't it 1 minus tangent squared? I don't have the thing written down. I would have to go and write it down to get the secant squared, what it would be equal to.
You're close. It's going to be tangent 1 and tangent squared aligned each other. Here's how I remember it. I know the Pythagorean identity, the cosine squared plus sine squared equals 1. You can get two other identities, multiple identities out of that. Oh, go ahead, Patricia. I saw you on mute.
I was going to say, isn't it tangent squared plus 1 is equal to secant?
Bingo. You're exactly right. That is the identity I want to use. To remember that, y'all, if you divided everything by cosine squared, you would get the identity that Patricia mentioned. The cosines will cancel out, giving me a 1. Sine over cosine will give me a tangent. So there's the 1 plus tangent. And then on the right-hand side, I'll get 1 over cosine squared, which is secant squared. And so if you're stuck and you don't remember, okay, what's that identity with the tangent? Go back to Pythagorean identity divide by cosine squared. But as Patricia mentioned, replace that with 1 plus tangent squared of theta. And now I have this. And now I am good to go to do a u substitution, with u being tangent and du being secant squared of x dx. So let's set that up. Let u be tangent. Then du is secant squared of x dx. I'm all good to go, so I'm ready for du sub. So integral tangent to the 4th power of x, 1 plus tangent squared of x, times secant squared of x dx by substitution is equal to integral of u to the 4th, 1 plus u squared times du. Distribute that u to the 4th. I'll get u to the 4th plus u to the 6th. I'm going to use my power rule that says add 1 to the old exponent to give me a new exponent, then divide by the new exponent. u5 over 5, u7 over 7 plus c. And because I did a u sub, I have to call back what u was at the very beginning. So tangent to the 5th power of x plus tangent to the 7th power of x. First one's divided by 5, second one's divided by 7, plus c. And that is my final answer for that particular problem. So to recap on this particular case, if I have a tangent secant integral, and if the power with secant is even, I'm going to take away a secant squared term, marry it with the dx, because that's going to be my basis for du. Rewrite the remaining secant squared portion by using my Pythagorean identity of 1 plus tangent squared equals secant squared. Do a u substitution, work it out to completion after that. Any questions about that particular example of that particular case? All right. And now there's one more case that we have to work with. And again, I'm going to illustrate this with an example. And here's going to be the example. So let's say I want to integrate yes. The part that I look for and that notes that I will have to do yes is if the power that is married with the tangent term is odd. That is going to be my deciding factor of when I'm using this particular version of this integral, of this method. So what I'm going to do is if I see the power married with tangent being odd, is I'm going to take a power away, but I am going to be selfish, and I'm going to take a power away from tangent, and I'm taking a power away from secant. And marrying that tangent and secant with dx. Again, I am doing that because I want that to serve as my basis for du. Because that is my basis for du, gives me a good indicator what u is going to be. So going back to Cal 1, what function do I know such that if I took its derivative, I get secant of x times tangent of x? So which trig function do we have that if I took its derivative, that would be its derivative?
Secant squared or secant?
Just secant, right? Just secant. So that means because I set that as my du, I want u to be secant. Well, that's good to go. That would be du. That's good to go because that will be u. This is not kosher. That is not good to go. I need to rewrite that tangent squared with respect to secant in order to take care of it. So I need to use a trig identity here as well. How can I rewrite tangent squared to be with respect to secant squared, or to secant? Which trig identity would I use?
Tangent squared equals secant squared minus 1.
Bingo. Thanks, Patricia. Secant squared minus 1. Again, to remember that trig identity, recall that in the previous problem, we got this identity by dividing it by cosine. Well, subtract both sides by 1, and we get that desired identity. All right, with that, we now have everything to go in order to perform the u substitution here. So let's get that set up. Let u be secant of x. Then du is secant of x times tangent of x dx. Therefore, what I now get as the integral secant squared of x minus 1 times secant to the 4th times tangent of x times secant of x dx. What I get after subbing is the integral of u squared minus 1 times u to the 4th du. Distribute that u to the 4th to the u squared minus 1 to give me u to the 6th minus u to the 4th. use my antiderivative rule for the power rule. And because I did a U sub, call back what I called you at the very beginning. So secant to the 7th over 7 minus secant to the 5th over 5 plus c. And that gives me my final answer for that particular problem. Right. I'm going to reach under my desk to grab my charger. Let me know if you have any questions about that. All right, so any questions? And so with that, that's trig integration in all of its possible cases. So now with this, the next topic that we got mentioned was series stuff. Yep, just series test. Any particular series test that y'all want to go over first?
Is all of them an option?
I second.
I'll go through all of them. Okay, well, let's first list out which tests we got so far. First, I'm going to do some rearrangement on my end underneath my desk because it is messy and I don't want that to happen again. So give me 1 second. There we go. I usually stand at my desk, so when I sit, I forget that I have to rearrange some stuff beforehand. So there we go. All right. So let's go through the test that we got right now. The first one I know we got so far is geometric. Second test I know of is divergence test. Third one that I got is the integral test. And the fourth one, not technically a test, but a method that we use to help us out, and that's telescoping series. So these are the 4 methods and tests that we have to help us evaluate and check for the convergence through divergence of a series. Only 4 we got as of right now. Or better yet, only 4 we got that will be on test 2. I know that y'all learned comparison test today, but since we learned it on Monday, that will carry over in test 3, not for test 2.
Is the P series on test 3 also?
Thank you for reminding me that.
Was it, no, last semester it was on test 2.
Thank you. P series will be on there. I forgot about that because it is a application of the integral test of how it's derived. So yeah, but P series test is on there as well. So in my opinion, the hardest part about series test, just like when y'all were doing integrals, is knowing when to use each particular test and when is each test appropriate. That's the hardest part. And so during this, I plan on covering first when to use the test, and then going over examples of how to do it and how to use each test. So first, geometric. First question I always ask is, when do I use the geometric series test? When would it be appropriate for me to use this particular method? And the way to answer that is based off what the series looks like. In particular, if the series looks like where I have some common factor, and if I see some ratio with k. So to interpret this is what I am looking for is I have a common ratio in my series. And so what I mean when I say a common ratio is if I have something being raised by a power that is dependent on the index of the series. It could be the exact same, which is like here with 6 bits to the k. And the exponents could be different, like here with the 2k plus 2 power or 3k minus 1 power. It does not make a difference. What I am looking for to know when I can use geometric series test is if the terms within my series have a common ratio with them, or I have a number as the base, and in the exponent, I have something that is dependent on the index of the series, both in the numerator and in the denominator. If I see that, that tells me that using the geometric series test will be useful here. So that's when I know when to use it. Any questions about that, about when to use the geometric series test? Well, next thing about series is once we establish which test to use, we also need to list down the conditions. Because for each of these tests, we have a set of conditions that we need to show that we satisfy in order for me to use that particular test. And so let's list out my test conditions for geometric series test. Condition 1. Find common factor A. That's why if you look in your textbook or in Dr. Bird's notes, that's why you see that coefficient A chilling there. That represents the common factor that is shared among each term within the series. The easiest way to identify what the common factor will be is figure out where your series begins, plug that number into K, and that will give you what the common factor A will be. So a couple of the samples. Let's go back to that 2k plus 2, 3k minus 1. I want to find the common factor amongst all of them. Here, my series begins at 1. So to find the common factor A, I'm plugging in 1 for K. So 2, 1 plus 2, 3, 1 minus 1. So in numerator, I get 2 cubed, 3, 0. So I get 8. So that tells me for this particular series, my common factor that I'm going to have is 8. Now keep in mind that this could change based on where the series starts. So let's get that same series again. 2k plus 2, 3k minus 1. Well, let's say that my series begins at 5 this time instead of at 1. Here, series starts at 5. So my common factor will be plug in where the series begins. Two seventh, 3 fourth, 2 sevenths would be 128. 3 fourth would be 81. And that would be my common factor for here. So first thing you got to do, find the common factor that all share. Easiest way to do that, plug in where your series begins for K, and that will be your common factor. Note that it is sensitive to where the series begins. That is important information I do need to know to find that common term. Here in this case, I had the same series, only difference was where it began, which meant I had a different common factor for each of them. So that's the first thing I needed to do. After you determine the common factor, next thing you need to do is determine the common ratio R. And the way to do that ask yourself, okay, which numbers have K living in the exponent? If it has a K in the exponent, it's going to be a part of R, or part of my common ratio for that. So let's go back to illustrate. And let's do the 2k plus 2, 1 again. 3k minus 1 again. here, the 2 and the 3 are the two components that have a k in the exponent. What that tells me is that 2 is going to play a part in the common ratio, 3 is going to play a part in the common ratio. So that tells me that R, or my common ratio, will be 2/3. Keep in mind that that ratio doesn't have to be positive. I could also have a negative one. So let's say, for example,
That's because you're gonna take the absolute value of it, right?
right. So I could have a negative, right. So that's where I have to take care of it.
Okay, thank you.
You're welcome. Okay. So let's say, for example, instead I had a negative 2 k plus 2 and then the 3 k minus 1. Well, that negative 2 has the exponent with a k in it, which means my common ratio would be negative 2/3 for that. Any questions there? Okay. We have the common factor. We have the common ratio. Now we need to explicitly state our winning condition, or what converges or diverges for the series. And so, as Davis mentioned, we're going to take its absolute value and see what that will give me in terms of here. If I get to that absolute value, there we go. If I get to that absolute value is less than 1, that tells me the series converges. If I get to that is greater than or equal to 1, that tells me the series diverges. So let's state that down. If it is strictly less than 1, converges. If that is greater or equal to 1, it's going to diverge. Now, granted, it might seem redundant, especially if your ratio is positive, say like at the 2/3. But I do need to explicitly state this condition because I'm trying to convince someone that I know this series converges or diverges. And this is the winning condition to state and know what will converge and what will diverge if I use a geometric series for that. All right. So again, conditions to summarize. When to use, if I see a common ratio with them. Test conditions. First things first, find a common factor by plugging in where the series begins. Next step, find a common ratio R by seeing what has a k in the exponent. If it has a k in the exponent, that's going to be a part of the common ratio. Next thing, take the absolute value for R. Note if it is strictly less than 1 or greater or equal to 1. Because that will tell me whether or not the series converges or diverges. Note that if the geometric series converges, this is one of the few series where I can actually calculate what that series adds up to. So if geometric series converges, then you can actually evaluate that series by taking whatever that common factor was, put that in your numerator, divide it by 1 minus the common ratio that you found. All right, so with that, any questions about geometric series test and that layout? Okay. So now what I'm going to give y'all is a problem to practice with. And I'm going to make this one up on the fly. So once I read it, give me a second to proofread it to make sure it's not too bad. And then I'll let y'all work on it. So 6. Yeah, that's good. All right. So the series I want y'all to play with and for y'all to try out is the sum, where my series starts at 6 to infinity of, and let's make this 7 look a little bit prettier, of 7 times 2 to the k minus 4 divided by 7 to the k minus 5 power. So I'll go ahead and let you know that this is a geometric series because I do have a common ratio, or I have a number with the exponent being dependent on the index of the series for that. So I want to give you all a few minutes to practice out the geometric series and to play around with it. I'll give you all a few minutes to try it. And when y'all are working on this, one thing I do want y'all to try and to practice with, make sure that you explicitly work out these 3 conditions. I didn't talk about them because I felt like to. I talked about them because these are necessary conditions that I need to show and explicitly state for me to use the geometric series test. So when you work this out, figure out what the common factor is, then figure out what the common ratio is, check for the convergence or divergence, and if you get convergence, tell me what the actual value will be. So this is the series we got. I'll give y'all a few minutes to work on it. If you have any issues or have any questions, let me know, and I'll be happy to help you out. And in about a few minutes, we'll work this one out together. So, okay. So let's get our hands dirty, and I'll give you a few minutes to work on it. Alrighty. Give me a status report, y'all. How are y'all doing on this problem?
I got an answer, but I don't know if it's 100% right.
Okay. How about the rest of y'all?
I feel like I got the right answer.
Okay.
I got the right answer.
I also got an answer, but I'm not 100% sure.
Okay. Well, in that case, let's dissect this guy and let's go through it. First, what would the common factor be for your series?
4/7.
I got 4 for A.
Yes, you got 4 as well. Okay, just keep in mind that we do have that extra 7 popping up there. So you're close. But 7 times 2, 6 minus 4, 7, 6 minus 5 equals 7 times 2 squared over 7. The 7s will cancel. And so I get 2 squared or 4 as the common factor. Yeah, but you're really close with the 4/7, but we do have an extra 7 being multiplied. So that's why we got that.
Yeah, for some reason I was thinking I could factor it out.
Got you. If you did this beforehand, then you would get 4/7 as the common factor if you just multiply your final answer by 7 at the end.
Yeah, that's what I did.
Okay. So if you did that, then you would get 4/7 as the common factor. You can also leave that 7 in the series and incorporate it in your common factor A as well. Either way, it would be correct at the end. Either or.
Okay.
So I should have stated that. So if you got 4/7 or 4 as a common factor, you're both correct. If you got 7, or if you got 4/7, then my guess is that the property y'all used was just like with integrals, just like with derivatives, and just like with limits. If I have a constant being multiplied to the series, I can factor the constant out and just look at the series itself. So either or would be correct here. So now step 2. What's my common ratio for your series?
2/7.
2/7, right. The K's appear at the exponents with a 2 and with a 7. So my common ratio here is going to be 2/7. Meaning, if I took the absolute value, I'll just get 2/7 again, and that better be less than 1. So I now showed it's a geometric series, common factor of 4 or 4/7, so you factored that 7 out at the beginning. Common ratio is 2/7. And if I took the absolute value, it's going to be strictly less than 1. So your series is going to converge by geometric series test. So I'm going to state a conclusion about that. So by the geometric series test, the series starting at 6 and equal to infinity, 7 times 2k to the 4th minus 7k to the 5th, it converges and this is one of the few times where I can actually get an actual number to converge to. So let me copy this back down. So what did y'all get as the number that your series converges to?
I got 28 over 5.
I got 196 over 35, but I think that simplifies. Or I think that's what I got. Oh no, let me go back and read.
All right. I believe it will be 28 over 5 afterwards.
That's what I got. I was like, those are so high numbers, so I'm not sure whether I got it right or not.
Oh, let's check. Common factor goes in the numerator. 1 minus the common ratio. 1 minus 2/7 better give me 5/7. Dividing by the fraction is the same as multiplying by its reciprocal. And that's where the 28 over 5 comes from. Let's use red to make a note that that is my answer. And there are my conditions for geometric series test. We stated this common factor. We stated this common ratio. We showed the absolute value for it is strictly less than 1. So geometric series test will tell me that that series will converge. And not only that, it tells me it converges to this particular number here. The 28 over 5. Any particular questions about data sample? So one of the next few tests we have is P-series test. Again, when you see a new series test, the first question to ask is when I can use it. And for P-series test, the way to know when to use it is if it has a very specific form. And the specific form is if the series simplifies to some series where I have 1 over k and is raised by some exponent p. If my series can be simplified to that form, that tells me that it's going to be a P series. With that said, let's go over to test conditions. And the test conditions for this guy is solely dependent on what that exponent P is. If that exponent is less than or equal to 1, then the conclusion we got is that my series will diverge. However, if I have that the series is strictly greater than 1, then I have that my series converges by P-series test. So P-series test is short, sweet, and to the point. I can use a P-series test if I can simplify my series down to have within the terms of my series 1 over K, or whatever the index of the series is, raised by some fixed exponent that I'll call P here. If I can do that, then that means I can use a P-series test, which says I look at that exponent. If it is less than or equal to 1, my series will diverge. However, if that exponent is strictly greater than 1, that series will converge to a particular number. And those are my conditions for that, for P series. And like I said, I'm using the language that simplifies to that form. You may be given that form automatically, you may not. The goal is, can I simplify down though to that form? So one quick example is k to the 7/2 power over k to the 5th. Now, that form, well, I don't know what to do with that, to be quite honest. But I can simplify that guy because I can use the property that says if I am dividing two numbers, same base with different exponents, exact same as me subtracting the two exponents together. Doing that, I will get k to the 7/2 power over 5. 5 is a fancy way of writing 10 over 2. So 7/2 over 10 over 2. That should give me -3 over 2. Now I have a negative exponent, so I can make that exponent positive by moving it to the denominator. And so for that series, not in that form 1 over k by some power, but I was able to simplify it down to be in that form. And in this particular case, my p will be that 3/2. And on a good day, 3/2 better be strictly greater than 1, which tells me that this series will converge. So let's state that conclusion. Since my p is 3 over 2, and that's strictly greater than 1, by the P series test, the series converges. converges to something? Well, it converges to something, but I have no idea what that number will be. So the best I can tell you is it converges to something. I don't know what though. Any questions here about P-series tests or that in general? Next test we got will be the divergence test. Now, for the divergence test, that's going to ask, is when can I use it? Now, I guess this is going to be a little bit different than geometric series and P-series, where I have a very particular form. And from that form, I could be like, oh, well, I know it's a geometric series and I know it's a P-series. For a divergence test, it's not that crystal clear with a particular form. And so the best way that I can determine when divergence tests will be used is check the limit of the terms in my series and just try to take that limit as k goes to infinity. And so sort of like when y'all learn limits in Cal 1, kind of the first thing that your professor taught you was first, plug in that value you're approaching the limit. Hey, is it continuous or does it make sense for that function? Answer is yeah. Good. That means you found the limit. Not good, then it's like, we should do something else. Kind of the same method here, the same thought here. I am just going to take the limit as a of k goes to infinity, and I'm just going to check what happens. And from that, my only test condition for the divergence test is if I took that limit and it does not go to 0. Now, it does not go to 0 means it could go to another number, like 1, -2, 5, 42, anything else. It could go to positive or negative infinity, or that limit may not exist. So either way, that's all encapsulated with that statement, limit of a of k does not equal to 0. If this happens, that is the only condition I need for the divergence test. If this happens, then I can automatically tell you that the series will diverge from that. Now, there are a few remarks that I do have to make about the divergence test, and it's because of common mistakes that I've seen before. So let's make those remarks. The first thing I want to emphasize, in that test condition, I did not say anything about the series converging. That was not me forgetting. That was on purpose. And that's because there's a reason why it's called the divergence test and not the divergence or convergence test, because there's only one thing it can tell you, and that's if the series will diverge. So first remark is that this test does not tell you if a series converges. So if you try to use the divergence test to conclude that a series converges, I'm going to go ahead and tell you that you're going to get a lot of points taken off on that problem, because that's not what divergence test tells you. It only tells you if it diverges, does not tell you anything about the convergence of a series. Only divergence of the series. To iterate that. And on that note, that follows up and talk about the second remark I want to make. And that is, I think the more common mistake that I see. If you get that the limit of k equals 0, of a of k equals 0, then divergence test is inconclusive. Series could converge, series could diverge. I don't know. But what that tells you is that you have to try another test. And again, remark 2 builds up from remark 1, because the common mistake that I see a lot of people make about the divergence test is say something like this. And I'll use orange to, since we're Clemson and I already wrote in purple, so let's fit with school colors. A lot of people like to say for divergence test, oh, well, the limit of k goes to infinity of a of k goes to 0, then the series must converge. That is the common mistake that I see. And I'm putting red because that puts the fear of God in everyone. That is a false statement. Just because the limit of the terms in that series equals 0, that does not tell you that the series will converge. As kind of an example, some examples to illustrate that point. Let's look at these two series. 1 over k squared and 1 over k. So for that first series, will that series converge or will that series diverge?
Converge.
Why?
By the P series test, it's greater than 1.
Okay, and what's P?
2.
Bingo. Yeah. The reason why I'm asked that, Matthew, is when you're doing and saying a series converge and diverge, my very first question will always be why. You say converge, I'll be like, why? And it's like, oh, because of this test. Why do you know that test? So that's why once you say converge or diverge, I immediately go, why? And say that. So that's a common thing that I will do to check. But right. Yes, guys, going to converge by the P series test because P is equal to 2, which is strictly greater than 1. So I'll write that in pink. What about that second series?
Diverge,
Okay. Diverge. Why will it diverge?
because it's simple harmonic motion.
Bingo. It's a harmonic series. Now, thing to note, I got one series will converge, other series will diverge, but if I take the limit of those terms within that series for both of them, I'm going to get 0 for both. However, the limit of the terms in my series for both of them, they both go to 0. But I have two different conclusions about the convergence and divergence of them. 1 over k squared, that's a convergent series. 1 over k, that's a divergent series. So I added that example to illustrate that just because you get that the limit of the terms as k goes to infinity equals 0, that does not tell you that the series will converge. That is a false statement. That's perhaps the most common mistake that I see with using the divergence test. And I do not want you all to make that mistake. So that's why I want to iterate that. So now, quick recap for divergence test. Kind of like with limits in Cal 1 when said, plug in a limit. Does it make sense if I plug in that number? Yeah, you're good. If not, you have to do something else. Well, here we could do the same thing. When you see a series and you don't know which test you should use, just try to take the limit of the terms as k goes to infinity. If you get that limit is not equal to 0, then you're good. That means you're done, because then you can say by the divergence test, the series diverges. If you get that the limit of those terms, however, equals 0, then it's like, oh shoot, I cannot use the divergence test here. So that means I have to move on and try another test to try that out. Any questions about that in particular?
I think I'm good. That makes sense.
Like I said, sorry for that rant, but I want to kind of reiterate. Be very careful with divergence tests. It's a very cheap and useful tool, but it is also very easy to misuse that tool. So with that, let's do some examples of divergence tests to illustrate. So I'm going to give out a few series, and y'all going to work it out and check to see if divergence tests can be used here. So first guy, 1 over k cubed, 4k cubed plus k equals 1, k to the 4th minus k 3rd plus k minus 2 over k 5th minus k 4th plus 7. Another one, give one more as practice for that. Ba, 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 ba. Those are my old notes for a good example. Oh, perfect. That'll work. Yes. Will that work? Yeah. Okay. So here are 3 series that I got. Question I got for y'all is determine whether or not I can use divergence test for these 3 series. So let's go through each one of them, starting with the first guy. First, let's try to take that limit of A of k. If I take that limit, what am I going to get if I take the limit of 1 minus k cubed over 4k cubed plus k?
Wouldn't it be -1/4?
Right. The nice thing here, I've said this to my class before. So if you're in my section of 1080, you've heard me say this before. If you're not, all tools from Cal 1 are now fair game in Cal 2. And here, from what I see an infinite limit of something that looks like a rational function. Highest power in the numerator is equal to the highest power in the denominator. So that limit will just be read off the coefficients that are married with them. And that's how we get -1/4. Again, all tools from Cal 1 are fair game here. So when y'all took Cal 1, I imagine the way that y'all learned it was you divided by the highest power in the denominator, simplified, and then took the limit at the very end. Since we are in Cal 2, we can now go for the main result that says I can read off the coefficients in that case. And because that limit does not go to 0, I can use the divergence test here. Any questions about that first series and about whether or not I can use divergence tests?
Since it's -1/4, it does diverge, right?
Yep. Doesn't matter what that limit is, as long as it's not 0, divergence test is good to go.
Okay.
Yep. That's sort of the nice thing about divergence test. Could be as long as it's not equal to 0, I'm good. Could be a positive number, could be a negative number, could be positive or negative infinity, or that limit could not exist. Either way, as long as it's not 0, divergence test is fair game. So let's now move on to that second series. First, let's copy that down. So for that guy, if I take that limit as k goes to infinity, what would that limit be?
Would it be 0?
Right, it would be 0. Infinite limit, something that looks like a rational function. Highest power in the numerator is smaller than highest power in the denominator. So that guy will shrink down to 0. Okay, so the limit of the terms equal to 0. So for that second series, can I use the divergence test here?
Because the limit of the series as it goes to infinity goes to 0.
Right. My God, I cannot spell. Right, the limit of that goes to 0, which means a divergence test. I don't know. Have to use another test to check the convergence and divergence of. Quick remark about that second series. It won't be on test 2, but we learned this today in our class, so I do want to talk about it. For this particular series, if I was going to check the convergence and divergence of it, I would use a comparison test. And the reason why I know that is because the terms in my series, they look similar to a rational function. Now, I don't want to say they are a rational function because these are the terms within a series, not a function we've seen in Cal 1 before. But I want to note that I would use a comparison test here because terms in the series do look similar to terms of a rational function. And the way I would form the series I compare, I would take the term with the highest power in the numerator, take the term with the highest power in the denominator, form the series I'm comparing with as the ratio of the two. Again, that's more of a TMI that's going to be later on in the course. But I didn't want to talk about that since we did cover comparison tests in our classes today. That for that particular series, I would use a comparison test on that for that particular reason. Now let's move on to the third series. So unlike the first two, doesn't look like a rational function here, but I can still use tools from Cal 1. In particular, I can use L'Hopital's rule here. Now, the reason why I'm thinking of L'Hopital's rule, if I took the limit of that numerator, that will be infinity. Take the limit of that denominator, that will also be infinity. So I have an indeterminate form of type infinity over infinity. And that is one of my two indeterminate forms that allow me to use L'Hopital's rule. So to evaluate, I would, by L'Hopital's, take the limit as k goes to infinity, derivative of the numerator, derivative of the denominator. L'Hopital's rule says, try again with the limit. But now here, they're the exact same. So I could cancel out. So I get to that limit is 1. And that is definitely not equal to 0. So for that third series, divergence test would be applicable here as well. It's just unlike with the previous two, where we can use our knowledge about kind of how rational functions work if we took an infinite limit. Here, I use L'Hopital's rule to help tackle that problem, which is another tool that we obtained in Cal 1. So here are our 3 series. First and the last one, yes, we could use divergence test. Second series, inconclusive. I would have to use another test in order to do that series. All right. Any questions about these 3 series and why I could and why I could not use divergence test on it?
Why would we use divergence test over any of the others?
The short answer, Natasha, is very cheap in terms of work. And what I mean by cheap in terms of work, all I have to do is take a limit, which in terms of, say, the geometric series test and the integral test and telescoping series, it's definitely a lot less work than those other tests for that, because all I have to do is take a limit. And also, sometimes it is very quick to see that if I took the limit of the terms in that series, it would not equal to 0. And so instead of doing all that nasty work I would have to do for, say, a comparison test or an integral test or the other test, I could take the very cheap route, say, oh, limit of the terms don't go to 0. Oh, good. I saved myself a hell of a lot of work by saying, by divergence test, the series will diverge. And so that's why divergence test could be beneficial in comparison to the other tests, because it is a very short and sweet way to get the divergence of a series if the limit is super easy to calculate, or I shouldn't say super easy, but very doable to calculate.
Thank you.
Yeah, you're welcome. Any other questions? Alrighty. We got 2 more tests. Integral test, and then the test is not a test, but more of a method, which is telescoping series. One thing I wanted to note, if you're studying right now or looking at the old test, that first series that you see, I got that from the spring 2020 old exam. And I believe that that problem is 2B. So if you want to know where that first series came from, that first series was actually an old free response problem where you did have to use the divergence test to show that that series does diverge. All right. So now let's move on to another test. And that is the integral test. First question to ask always when you see a new series test. Is when can I use that test? And the answer to that is if it would be very doable to take the integral of that terms in the series. So let's say I have an arbitrary series A of k. Let's say if I formed the function f of x by replacing everywhere I saw a k in the series with x, then I would use the integral test if that integral is doable, meaning if I formed a function by replacing the indices k with an x in my series, and if that integral is very, very doable, meaning that I don't have to do anything crazy to that integral, I can use the methods that we learned in class, then I will think about maybe using integral test to evaluate and to check the convergence or divergence of a series. Now, for the test conditions of the integral test, this is a lot longer than with the geometric series test, the p-series test, the divergence test. This requires a lot more work before we could do anything and check the convergence and divergence of. So the first thing I have to do is I have to make some checks on the function itself. And here are the checks I make. First, let's go ahead and make his notes. I formed the function f of x by replacing everywhere I saw the indices k with the variable x. And now my domain for this function, to kind of illustrate, I'm going to go ahead and say that the domain of this function is going to be from 1 to infinity. The reason why I'm getting that as my domain for the function is because I started my series at 1, I finished my series at infinity. So That's why I have my domain to be from 1 to infinity because of that. If my series started at like 4 or started at 3, I would adjust accordingly and say 3 if my series started at 3, 42 if my series started at 42, so on and so forth with that domain. And so here are my 3 precursor conditions I needed to show before I can even do integral test. Condition 1, I need to check if f of x is positive for every possible value for x in my domain. So that's condition number 1 I need to check. Is my function f of x positive for any single x that I could do in my domain? .99% of the time, this will be a gimme because it'll be very obvious if that function f of x is positive everywhere or if it's negative somewhere. But I still need to state that because, again, I'm trying to convince the reader why a series converges or diverges. So I need to state that because it's one of my winning conditions. Condition 2 that I need to satisfy is that f of x is continuous for all x in domain. Here, the way that I would verify that is say, okay, if there was going to be a discontinuity, where would the discontinuity be? And make it clear that, oh, that discontinuity is not in the domain. So for example, let's say the function that I formed after I replace all of the k's with x is x over x plus 1. Now, the only way for that function to have a discontinuity is if the denominator equals to 0. And the denominator equals 0 if x equals -1. So first we'll state f of x is discontinuous at s equals -1. And while that sucks that I do have a discontinuity, I'm not worried about it because that point -1 is not even in my domain. So even though I have a trouble point at -1, it's nowhere in the domain that I have to worry about. So that means, yeah, even though there's a problem point, I'm still Gucci because of the domain I formed. So I'll make that as a note. Not in domain. So I do not have to worry about it. So I would verify condition 2 by saying, okay, where would the discontinuity be? And then make it clear that discontinuity is not even in my domain to begin with. So I don't even have to worry about it. And then the condition 3 that I need to show for the integral test is that f of x is decreasing in my domain from 1 to infinity. Now, to show decreasing, the easiest way that I could think of to show decreasing is to use a tool from Cal 1. And that tool is that first derivative test. And so let's recall that. So when we learned the first derivative test back in the day, first derivative test tells me what about the function decreasing. If the function is decreasing, what must happen to its derivative? Or for me to use first derivative test to show decreasing, what must I show with the first derivative? Do I need to show as positive? Do I need to show as negative? Do I need to show anything else about it?
That it's positive.
Gotcha. You're close, Davids. If the derivative would be increasing, or derivative is positive, my function would actually be increasing. And the reason why, kind of give a brief recap, is if I drew a tangent line wherever that function was increasing, that tangent line would have a positive slope. And one of our interpretations of a derivative is the slope of that tangent line. So if we're decreasing, first derivative test tells me I need the derivative to be negative. And again, to recall from Cal 1, if my function is decreasing, then my tangent line, anywhere where it's decreasing, will have a negative slope. And one of our interpretations of the derivative is that the derivative is the slope of the tangent line. So if I look at where that function is decreasing, my tangent line will have a negative slope, which means its derivative will be strictly negative. So the best way to show that my function is decreasing for the integral test is to use the first derivative test as a tool and say, I take the first derivative. Is my first derivative negative everywhere in that domain? If I have that, that tells me, that the function is decreasing in my domain. And with that, I'll have conditions 1, conditions 2, and condition 3. And for me to even use the integral test, I do need to check all 3 of these conditions to holding in order to do it. After I check that those 3 conditions are satisfied, then we do what the namesake for the integral test, which is now we evaluate that improper integral. And what the integral test says after you check those three conditions, whatever happens to that improper integral, that will also happen to the series itself. So let's summarize. So if that improper integral, if it converges, then that series will also converge to that exact same point. Now, vice versa, if that improper integral diverges, then so will the series itself. So, to summarize, I would only want to do the integral test if that improper integral is doable in the first place. My test conditions for the integral test is, I first define a function f of x by replacing everywhere I saw a k with x. Define my domain to be where the series begins to where the series ends. And then I have to check three conditions. Condition 1 is that my function is positive for all x in the domain. This one is usually a gimme, so we don't have to think about that too much, but we do need to state it because it is a condition for us to win. Condition 2 says that my function f of x must be continuous for all x in the domain. Best way that I can think of to verify that is first say, okay, well, let's see if there is a point of discontinuity. If you do have a trouble point like that, then you'd be like, okay, well, is it in my domain? And if it's no, okay, then we're still good. We might have a trouble point, but it's not my domain. So I do not have to worry about it. Then I go to condition 3, which is to check that my function is decreasing in my interval. And the quickest way that I can think of to do this is to use the first derivative test to state that the derivative is negative 4 points in my domain for that. Only after I check conditions 1 through 3, then I would use the improper, then I would take the improper integral. And what the integral test tells you is if the improper integral converges, then the series will also converge. Vice versa, if this integral diverges, then the series will also diverge. And that's what the integral test can tell me from that. Now, like I said, this is a lot of work to verify, to do the series on one particular test. That's why my suggestion is, say you guys series off the blue, is to only even think about using integral test if that improper integral is very doable, meaning it's not super complicated. All we have to do is to use basic tricks that we learned throughout the course in order to evaluate that. Only then when I'd be like, okay, maybe the integral test could be doable and useful here. But I would need to check these three conditions are satisfied in order to do that. Any questions about any of those conditions? Any about that at all? Yeah, like I said, out of all the tests and methods, this is probably, I think, the most complicated one that you will see on test 2. And also the one that requires the most amount of work for it. So and now with all that said, let's do an example problem. So I'm going to pick one because this is already nasty as is. I don't want to make up a ugly one right off the bat. This will work. Okay. So let's say this is the series that I want to work with. Let's say not told anything. I'm just said check if the series converges or diverges. First thing that I would note to check if the improper integral is doable is to check the antiderivative of it and see if it's doable to do. In this case, it will be doable because I could do a u sub where u is negative 4x and du is negative 4 dx. Plus c, negative 1 4 e, negative 4x plus c. So my thought is, okay, well, if I just took the improper integral, that integral is very doable. I don't do anything crazy to it. I just use basic tricks that we learn throughout the course. So that tells me if I see a series out of the blue that the integral test might be a valid candidate for it. So let's get everything ready to go as if we were doing the integral test. So first, let's define a function f of x to be wherever I saw a k in the terms in this series, replace with x for that series. What would the domain be for that function?
One to infinity.
1 to infinity. Now, why 1 to infinity and not say like 700 to infinity or -2 to infinity? Why 1 to infinity?
Because the sum starts at 1.
Bingo. Series begins at 1. So that tells me my domain should also begin at 1. Very good. So I now have the function. I'm now ready to check my necessary conditions for the integral test. So the first condition, f of x positive. Like I said, this one is a gimme. The answer here will be yes. And the reason why is recall that an exponential function will always be positive no matter what value I plug in. So I'll actually say yes. Recall that exponential function is positive no matter what value I plug in. And e to the -4x is just 1 over e to the 4x. Numerator is always positive. Denominator is always positive. So that entire function better always be positive as well. Next thing we need to check is my function continuous for all x's in my domain? So the way to check is in my denominator, I would have e to the 4x. Well, only way for that to be discontinuous is if that's equal to 0. And here's kind of my question before I do any work. Is that even possible? Is it possible for an exponential function to equal 0?
No.
No. Recall that for an exponential function, my domain is any real number I could think of, and my range, or my possible outputs, is any positive number. Where 0 cannot be a possibility. So you asking me whether or not I can have an exponential equal to 0, is that possible? The answer here is no for that. To further convince why that can't happen, let's say I was going to try to solve it. Solve for x. Well, first I have to get rid of the exponential, which means I'll have to take the natural log of both sides. Which means on the right-hand side, I would have natural log of 0. Well, that's a very big issue right now because domain of the natural log is all positive numbers. So what I just did was I just plugged a number that is outside the domain of that function. That cannot happen. So because of that, having e to the 4x equals 0, that's not possible at all. Which means my function f of x has no trouble points, nothing to worry about. So my function is continuous everywhere in my domain. Any questions about that explanation about f of x being continuous everywhere?
Why did you set it equal to 0 again to make sure that it was continuous?
Can you repeat that again, Davis? You kind of cut out near the end.
I said you just set it equal to 0 to make sure it was continuous.
Right. So I set it equal to 0 to see if there was a problem point. And if there was a problem point, I wanted to verify that it was not in the domain. So that's why I set the denominator equal to 0 to essentially say, does my function have a pointed discontinuity? And if so, is it in my domain? For this particular example, I don't even have a pointed discontinuity because if I did, can't even happen. And so the quickest way to check that is to set the denominator equal to 0 and see what would happen.
Okay.
Yeah, so that's why I did all that work below to see if there was a trouble point. And now the third condition is f of x decreasing in my domain. Again, quickest way I can think of to check is do the first derivative test. So for my function e to the negative 4x, what would that derivative be?
Negative 4e to the negative 4x.
Yep. And so let's check if that is negative. Numerator is going to be a negative number always because it's negative 4. Well, you just stated here that I have an exponential function which will always be positive. So my denominator is always going to be positive. Negative number always divided by a positive number always will mean I will always have a negative number. For all x. So my third condition for checking if f of x is decreasing is a yes. So conditions 1, 2, and 3, they are all good to go for me to do the take the improper integral. So conditions 1 through 3 are met. We now get the improper integral. So integral from 1 to infinity e negative 4x dx. Recap from improper integrals. Very first step, what do I need to do before I even begin evaluating?
Make it a limit.
Okay. Take a limit of what?
A going to infinity.
Bingo. Can't take that integral if I have an improper or an infinite limit. So I have to rewrite it so I can do that. So as Matthew Davis mentioned, I'm going to call it a dummy variable. You can call it whatever you want as long as you define it. And then state that I'm taking that limit as a goes to infinity from 1 to a. Like I said, you could call that dummy variable whatever you want. Let's make it clear that's an a. That looked ugly. Fun story. When I was an undergrad student myself, because I was a weirdo, I would call my dummy variable a Pokeball. And so I would just have that be limit as to Pokeball goes to infinity and just work my way around with Pokeballs everywhere. Please do not do that on the test because your grader may not have as much humor as I do. But that's just to illustrate that. As long as you state what that dummy variable is that you use for your improper integral, you can use whatever symbol you want as long as you define it. So you can use A like we did here. You can use T. You can use B. You can use Pokeball. You can use a smiley face. As long as you got that defined, you're good to go. So let's keep going. Limit a goes to infinity. So wanting to note, because of notation, as soon as you introduce that limit stays with you throughout the rest of your evaluation of that integral. So as you keep on going, that will have to remain with you until you're at the evaluating the limit step. So if you drop that limit notation somewhere, you will lose notation points because of that. So, I don't want you to go back down. Thank you. So integral. We worked on this antiderivative before. -1/4 e to the -4x. And fundamental theorem of calculus says evaluate at the upper limit subtracted by evaluating at the lower bound. One thing I want to point out for improper integrals, because this is a common mistake I've seen with improper integrals, and that's if you do a u sub while you do an improper integral. Even though you have a dummy variable a, that is still a definite integral. And so because it is still technically a definite integral, just like how we learned u sub for definite integrals at the beginning of the semester, I do need to change my bounds when I do a u sub for a definite integral. So I want to reiterate that here, that even though I do not know what a is specifically, this is still a definite integral I'm working with. And so because of that, if I'm doing a u sub on on an improper integral, I do have to change my bounds if I do that. So limit a goes to infinity, antiderivative evaluated at the upper limit minus antiderivative evaluated at the lower limit. -4 times 1 better give me a -4 minus a negative number, better change that to a positive number. One property we have of limits is that the limit of a sum and difference of two things is the exact same as me taking the limit of the first term, limit of the second term, adding and subtracting at the end. So that's what I'll be doing here. And now I evaluate the limits. Second guy, I don't have an a anywhere with the 1/4 e to the -4. So that's just a constant. And limit of a constant means I do nothing. So I'll just be 1/4 e to the -4 at the end. For that first term, what will that limit be if I take the limit as a goes to infinity?
Would it be 0?
It would be 0. You're exactly right, Matthew. Kind of illustrate why. I do have a negative exponent. I could change that negative exponent to a positive exponent by moving it over to the denominator. So as my inputs get super large, my denominator, because it'll have an exponential, will also get super large. And what that means is that my whole fraction will get super duper small because the denominator is getting super large and it's getting to 0. So that's what's going on and why that goes to 0. So let's summarize. My improper integral that I just formed, we did all of our work and we concluded that I get to a finite number. So my improper integral converges. And like we stated with the integral test, whatever the improper integral does, the series will do as well. So since I converge, that means my series is also going to converge. So let's state that conclusion now. Since the integral from 1 to infinity of e to the negative 4x dx, because you showed that that converges, then by the integral test, the series sum k equals 1 to infinity e to the negative 4k also converges. And that will be my final answer for that particular problem. Any questions about that problem in particular and kind of going through the dot process for that problem?
So that integral, that series does converge, but the integral test doesn't mean that it converges to that value, right?
Correct. That value that the integral converge will not be the same point that the series converge to. That is a very true statement. And so one quick example to kind of see why. Is 1/2 of x and 1/2 of k. Now that series, yeah, I could use geometric series test and get that very quickly. And if you do, you get that equal to, actually, I got a better example for y'all. So let me change that real quick. Mainly because this is a cool fact. If you evaluate that improper integral, you're going to get to that equals 1. However, for that series, the mathematician way back in the day, I think it was Euler, he showed that that series actually equals to pi squared over sets. So, like you said, Matthew, it's true that if the improper integral converges, so does the series. What is not true is that they converge to the same number. That's definitely not a true statement overall. So you're correct with that. Davis, do you have a question? Any other questions about that sample?
Can you hear me?
Yep, I can hear you now.
Okay, so sorry, my headphones weren't plugged all the way in.
You're good.
So whenever you equal 0, if you scroll up a little bit, yeah, where it says equals to 0 plus 1/4 e to the negative 4, that is just straight. That's just a straight up 0. It's not like the There's another test where it's like if it equals to 0. I think it's geometric series where if one part of it is equal to 0, like it diverges. Therefore, the whole thing diverges.
Gotcha. I think you're taking a divergence test, which again, be careful. because if the limit of the terms equals 0, I can't use divergence test. Here, I'm not even thinking about series right now. I'm just working with the improper integral. And so I don't have to be necessarily that careful within, let's go back up, within here, down. I'm just evaluating the limit as we have back in the day. So I don't have to be careful about series or anything. It's just my work for the improper integral portion. So I don't need to be careful about that.
Okay, thank you.
You're welcome. All right. Any other questions about that? All right. So on my clock, I have that as 9:11 p.m. The reason why I'm pointing that out is I do know that the Calculus Fight Club is running now. Just to let y'all know. And so I don't necessarily want to overlap the Calculus Fight Club. And so because of that, I will end my review here and say that if you still want to study tonight, the Calculus Fight Club is going on tonight from 9 to midnight via Zoom.
Are you gonna stop in there like you did last time?
No, that was more of one of my friends told me about something, and so I decided to pop in to see what was going on.
It'd be